All right, so that was classical distributions. So now let's consider quantum statistics. So typically, just let me reiterate. So classical results should emerge from the quantum mechanics. And the previous classical arguments are valid whenever the quantum effects are not important. And when quantum effects are not important, we can basically characterize that by so-called wave function overlap, when wave functions of distinct particles start to overlap. Quantum effects and basically indistinguishability becomes important. And now let me remind you how quantum mechanics influence the occupancy of states. Like suppose we have two particles, 1 and 2, and two states. Let's call them A and B. And let's try to write wave function for distinguishable particles and indistinguishable particles. So for distinguishable particles, let me write it like psi m, which is going to depend on 1 and 2. You can have psi one particle in A and second particle in B, right? They are distinguishable. That's like a valid state. And I put M here for like Maxwell-Boltzmann. Even though this is quantum, I'm going to label it like this. For indistinguishable particles, I have two possibilities. I can have bosonic particles. Then let me put it, bosons 1, 2 is going to be equal to 1/2 first particle in A, second particle in B, or exactly the same way, but first particle in B, second particle in A, first particle in B. Right? So this is the bosonic case. Or we can have, like, again, indistinguishable particles, but with half integer spin, which is going to be fermionic. So let me just copy this. It's exactly the same. And this is going to be minus, right? We considered this before. If not, you can just try to, wherever you see 1, write 2, wherever you see 2, write 1, and show that psi sub B is anti-symmetric, symmetric, and psi sub F is going to be anti-symmetric. Show this if you can't remember that. So then now let's consider what is the likelihood of having both 1 and 2 in a given state, which is the same. Let's call them A. So the distinguishable case is like simple, right? I'm just going to, so this is case I. I'm just going to write the labels, and there's no problem with that as long as we don't have distinguishability. But in the bosonic case, I'm going to have what? I have A1, A2 plus A2, A1. So first term is exactly the same as the second term. So I can just multiply the entire, I can just take first term and multiply it with 2. So this is case 2. And there's like 2, right? 2 divided by square root of 2 is going to be root 2. And you can see root 2 is bigger than 1. Here is I have 1. So in the bosonic case, the occupancy of the, okay, this is A, occupancy of the state increase due to bosonic statistics. And lastly, we can do exactly the same thing for fermions. Let me just copy this. And if I put all A's and B's equal, so this is A and A, you can see this is something minus itself, and this is going to be 0. So in the bosonic case, you have enhanced the occupancy. You are more likely to occupy a state if there is already a state there. In the fermionic case, you are not likely to occupy it again. So there is only one particle per state, and that's Pauli principle. Okay, so in the quantum statistics, then presence of a particle in a state modifies the probability to have a particle in that state because of this observation. So again, without exactly like classical case, so if you remember, I didn't show it, but I gave you a hint for next years. You start from W and you optimize W subject to constraints, and you find, for example, Boltzmann statistics. You can do exactly the same calculation. You can calculate W, but with bosonic or fermionic statistics, and you can optimize to find the distribution functions, and the result is, let me just write it. So F, so the bosonic case, so let me call this F, this is Bose-Einstein distribution, is 1. So exactly like a constant, there was like, if you remember in the Maxwell-Boltzmann, there was like a times e to the minus epsilon over kBt. There is also a constant here, but we write that constant in a funny way. So let me just e to the alpha, this is the constant, e to the alpha, times e to the epsilon over kBt minus 1. And so you can see like in the classical limits, like if energy is large, I can forget about this, right? If energy is large, e to the something large is a large number, and I can forget about this, and this is going to go to e to the minus e over kBt. So it satisfies the classical distribution in the large energy limit. So this is a check. And this minus 1, okay, let me also write the other one and then let's compare. So F, the other one is, so this is bosonic, this is fermionic. We call it Fermi-Dirac distribution, and it's going to be exactly the same thing, but it is plus in between. So also, if you want to remember it, like, so you can see there's like a minus, right? Minus 1 is going to decrease the value of numerator, and its smaller numerator is like bigger f. So you can see f is going to be bigger for bosonic, whereas plus 1 in the denominator here is going to increase the denominator, and f is going to decrease. So in the fermionic cases, you are going to have like a decreased probability to see the particle in that state. So this is increased likelihood, and this plus 1 is decreased. Okay. So also, if you look at this carefully, and you can forget about this for a little bit, but at the end, suppose alpha is equal to 0, epsilon is equal to 0, you have like something always less than or equal to 1 here, right? There's no way this quantity can be like bigger than 1. So this is the Pauli exclusion, whereas we don't have such a thing here, right? If you have like alpha is equal to 0 and epsilon is equal to 0, you have 1 minus 1, 1 over 0 is going to blow up. So in that limit, alpha is equal to 0 and epsilon is equal to 0, it seems like occupancy blows up for boson case. There's like infinitely high likelihood of occupying the state in that limit. Whereas in the fermionic case, it's always less than or equal to 1. So let me draw a graph of how these functions look like. So this is epsilon, and this is f of epsilon. So you can see, like in the Maxwell-Boltzmann case, as epsilon goes to 0, you are going to go to a constant, right? There is like some constant here. And as you increase the energy, e to the minus infinity is going to be 0. It's going to go to 0. So this is Maxwell-Boltzmann. And in the bosonic case, as you go to smaller and smaller energies, you need to blow up. So it's going to be more likely to occupy that state. So it's going to be something like that. So this is Bose-Einstein distribution. And in the case of Fermi-Dirac, as you go to smaller and smaller energies, you can see, okay, this can be something like 1 plus 1 is like something like less than 1. But we'll see in a little bit in the smallest energy and 0 temperature limit, it's going to go to 1. So it's like something like that. There's like a 1 here, and it goes like that. So this is Fermi-Dirac case. Okay. Mm-hmm. Yes.
And the other one had half the speed.
Yes.
So this is telling you the distribution, the probability distribution differs for those half and.
Yes, exactly. That's exactly what we are saying. Whether.
I didn't understand the part about the wave function.
Mm-hmm.
What is the reason?
So the reason is coming from this, right? Because the wave function has to be symmetric or anti-symmetric. For example, in the integer case, it has to be symmetric, right? Or in the, I think it's easier to consider it in the fermionic case. It has to be anti-symmetric, and that means if a state is occupied, it cannot be occupied again. Whereas in the classical statistic, if a state is occupied or not, you can always put more particles in that state, right? Doesn't matter. You don't have any symmetry requirement. And this constraint, like whether you have a particle in a state already or not, is going to modify this multiplicity W here, right? If you want to calculate all possible configurations, inside all possible configurations, you need to put that symmetry constraint on top of this total energy and number constraint. And it's going to give you this quantum statistics. I mean, we didn't do it. It is not like a very difficult calculation, but it is subject of another course. So I didn't do it, and I just give you the result here, which is this one. Any questions or comments? So exactly like the Boltzmann case, this alpha can be found. Alpha can be found from normalization. Basically, you just sum all particles with all energies. It should give you the total energy. And n of epsilon. But in that case, the integral is a little bit more difficult. So this is the integral you were talking about. But typically, we just give these integrals. Like we give you the result, and you don't spend 30, 40 minutes in like an exam to calculate those integrals. And here again, n of epsilon is g of epsilon, f of epsilon, and here f can be this one, Fermi-Dirac, or Bose-Einstein statistics. So if particle number is not conserved, is there like an example to this system? Can anybody think of a system where particle number is not conserved? In which system can you increase or decrease number of particles? Photons, right? So in a cavity, did you say photon or something else? Okay, so in a cavity you can always increase or decrease it, right? Cavity can absorb photon and destroy it, or it can spontaneously create photon and increase it. If the particle is number, in a case like this, if the particle number is not conserved, alpha is generally 0. So you'll see this is going to be related to something called chemical potential, but let me not get into that to scare anybody. So this is also related to something called Fermi energy. Let me introduce that. Fermi energy. So when a Fermi-Dirac distribution becomes exactly 1/2, so this defines the Fermi energy. And for this to happen, you can see if this is exactly 1/2, this thing should be 1, right? So this thing should be 1. And if this is 1, what is the condition between alpha and epsilon? So alpha plus epsilon over kBt should be what for this to happen? 0. Then E, which is defined by this equation, we call it E Fermi, is equal to minus alpha divided by kBt. And then this distribution can be written epsilon Fermi is equal to minus alpha. Yes. This is minus alpha kBt. Yes, correct. Okay. So if I want to write it in terms of this, now you can see I related alpha to another constant which I called, so this is called Fermi energy, and this is going to be 1 over e to the epsilon minus epsilon Fermi kBt plus 1, right? Now, okay, I think minus epsilon Fermi divided kBt is alpha, so that's correct. So let's see how what this function look like. The easy limit is t is equal to 0. So t is equal to 0. Then if epsilon bigger than epsilon Fermi, I have something positive, right? Because epsilon is bigger than epsilon Fermi. That's what I'm assuming. And divide something positive with 0, you are going to have infinity, and you can forget about 1. 1 over infinity is going to be 0. So f Fermi-Dirac is going to go to 0. And if epsilon is less than E Fermi, in that case you have something negative, and something negative, right? Because epsilon is less than epsilon Fermi, epsilon minus epsilon Fermi is negative. Negative divided by 0 is going to be minus infinity. E to the minus infinity is 0. So you can forget about this. 1 over 1 is 1. So f Fermi-Dirac is going to go to 1. And the function looks something like this. So this is f Fermi-Dirac of epsilon. So this is epsilon, and there is like some special energy which is E Fermi, and until you reach this you are 1, right? 1, 1, 1. As soon as you reach here you are going to drop to 0, and you are going to be something like this. Now if you increase the temperature a little bit, if it is not exactly 0, you are going to have something like this, but it's going to be a smooth crossover from here to there. Maybe I can show So a couple of examples. Maybe you go something like that. Something like that. So this is T non-zero but still small. Maybe something like that. And something like that. And so this is, by the way, F Fermi-Dirac of epsilon is going to be equal to E Fermi minus epsilon at t is equal to 0. It's basically a step function. Good. Any questions or comments? So at 0 temperature, what happens is like you are just like you have some available states, right? Infinitely many, and you fill one particle per site. Maybe because of spin, 2 particles per state, and then you exhaust all the states. At some point, distribution goes from like 100% occupancy and 0% occupancy, and this maximum energy is Fermi energy. And you minimize the total energy by doing this for the electrons. Let's also consider what happens for the case of bosons. Let's consider the bosonic case. So as you can see, in the bosonic case, what's going to happen is as you go to smaller and smaller temperatures, maybe I can tell you what happens and then explain you more physically. This alpha goes to 0. Okay, as t goes to 0, alpha goes to 0. This is 1, and you can see it will be more favorable to occupy the lowest energy, which is the 0 energy, right? So it's going to be like something like 0, and e to the 0 minus e to the 0 is 1, 1 minus 1 is 0, 1 over 0 is infinity. So you have like infinitely many states, infinite occupancy of 0 energy state.
Is it for t to 0 or t to infinity?
F goes to infinity, right? As
e
t.
to 0 as t goes to 0.
So it was e to the alpha, e to the epsilon over kBt. If t goes to 0, I'm only going to pick up the smallest energy, which is 0, right? E to the 0, and t will be very small, but still non-zero. So this one is going to be 1, and this one is going to be something very close to 1. Something very close to 1 minus 1 is going to be a very small number, and it's going to blow up. So this is like an infinite occupancy in 0 temperature limit. So what happens is like, let's consider like n bosonic atoms in volume V and temperature T. So that's the correct statistical variables I need to consider. And from like equipartition, I know average energy is what? For like in 3D, based on what we used in the first lecture, 3 over 2 kBt times n, or I can consider like average energy per particle and I absorb it inside epsilon, something like that. And I want to equate this. Okay, I want to like see when this classical behavior transitions to quantum behavior and this weird thing takes place. And this, for this, I'm going to equate this to p squared over 2m. It should actually be p expectation value, but let me not write that. Then from here, p is going to be equal to, cancel 2, 3m kBt, and this is square root. And if I have the momentum, I can relate the wavelength, right, from de Broglie, like using the Broglie. Lambda is equal to h over p. This is going to be h over 3m kBt, something like that. And now I have like wave. Okay, here's my container, something like that. And I have these individual atoms, and each one have is de Broglie wavelength. And you can see as t goes to 0, de Broglie wavelength is going to go to infinity, right? It's going to go to larger and larger values as you go to smaller and smaller temperatures. But at some point, these waves are going to start, right, overlapping, something like that. Of course, this is like a caricature, but I think you can convince yourself something strange is going to take place when this happens, right? And when these waves start overlapping, they are going to do interference, right? They are going to start combining. And whenever lambda is order of d interparticle spacing, maybe I'm going to have like a giant wave. And let's calculate when this happens. And after that I'll finish. So this is lambda over this. And this is equal to d. And for d, I'm going to use this. Density is number of particles divided by volume. Then for average interparticle spacing, I'm going to take volume and find average volume for each particle, right? This is the average volume for each particle. And I'll take 1/3 of this to find the typical distance. And it's going to 1 over n 1/3. And you can see this is defining like a TC. So this is like, let me call this TC. TC is equal to h squared n to 3/3 divided by 3m kb. Did I miss anything? Hopefully not. So this is the critical temperature for giant matter wave. And this is when this lowest state is occupied macroscopically. Right? The smallest possible energy is occupied macroscopically, and you have a macroscopic gigantic wave, and that's what we call Bose-Einstein condensates. So this is Bose-Einstein condensate temperature. Okay, maybe I can stop here. Any questions or comments? And all right, thank you.